sigma 3. Okay. Now, immediately whatever we can fill, we will fill. E C3, C32, sigma 1, sigma 2, sigma 3, C3, C32, sigma 1, sigma 2, sigma 3. Okay. So, we could fill this immediately. Just to keep track, I am drawing this grid. Now, C3, it should be C32, right? By definition, this is C32. C3, this is 240, this is another 120. So, it will become an identity. So, we can immediately write this, and C3 is an identity. C32 is C3. So, this part of the table we can fill. Similarly, sigma 1, what will that be? Sigma 1 is a reflection. If you reflect 2 times, you will get back to the identity. So, sigma 1 is identity, sigma 2 is identity, sigma 3 is also identity. Okay, we can fill that one. So, what are all the non-trivial things? These 6, and these 4. So, 10 we have to fill, and they are little bit non-trivial. So, how to fill those things? Now, the procedure is something like this. I think I require some space. Okay, so let me just show you one of them. For example, I want to know what is C3 sigma 1. Okay, that means what I am going to do, maybe I will write here C3 sigma 1, this is acting on actual identity, okay, the structure. What will sigma 1 do? First, I will operate sigma 1 on this. This will make this 1, 3, 2, correct? 1, 3, 2. Now, what will C3 do on this? Rotate by 120 degrees counterclockwise. So, this becomes 3 will come here, 2 will come here. So, 2, 1, 3. Now, what is that among these things 2, 1, 3? Sigma 3. Correct? So, C3 times sigma 1 is sigma 3. Okay. Now, I can do this exercise, but then I can also use rearrangement theorem, because I know that each column and row should occur, every element should occur only once. So, sigma 3, sigma 2 cannot occur here. So, it has to sigma 1 and sigma 2. So, I will fill this. You know how rearrangement theorem helps us, but you can verify by doing this that these are the things that we have. Now, any one of this I have to verify, and then other things I can write. So, let us ask what is sigma 3 2 sigma 1. So, C3 2 sigma 1. So, this is C3 2. C3 2, what will it do? This will go here and here. So, this will be 3, this will be 2, and this will be 1. So, 3 2 1. So, what is 3 2 1? Is sigma 2, correct? Of course, I do not have to do that also, but let me put this is sigma 2. Okay. Now, I can put sigma 2, sigma 1 is already there. So, I have to write sigma 3 and sigma 1 here. So, I have filled these things very easily. Now, I ask what is sigma 1 sigma 2 or sigma 1 C3. So, sigma 1 C3 sigma 1 C3 of 1 2 3, that is equal to sigma 1 3 1 2. But remember, when you are putting the sigma 1, you must keep the mirror here only. Since 1 came here, you should not put the mirror here. The mirror location is fixed, only these labels are changing. The point mirrors are fixed. So I must take a sigma 1 is this mirror. So that what will you get? You will get this as 3, 2, 1. So 3, 2, 1 is sigma 2. So I will get sigma 2 here, which means I have to get sigma 3 here. Okay, and one more, sigma 2 to sigma 3 if I do. So if I take sigma 2 here, so 2, where is 2? 2 is here, so that means this one. So this gives you so 1, 2, 1, 3. 2, 1, 3 is sigma 3. So this is sigma 3. So this is sigma 1. Immediately I can fill up. This is sigma 1. This is sigma 2. So this is from rearrangement theorem. I can immediately write this. And here what all should get? These 3 and these 3. They cannot be sigma 1s. They have to be only C3, C3 2s. Correct? So sigma 1 into sigma 2. If I do that, sigma 1 into sigma 2. Sigma 1, sigma 2 on 1, 2, 3 is sigma 1 on 3, 2, 1, which is equal to 3, 1, 2. So 3, 1, 2 is C3. So this is going to be C3. So this has to be C3 2, this has to be C3, this has to be C3 2, and this has to be C3, this has to be C3 2. So I can fill up other things by using rearrangement theory. So this is, now what do we understand from here? From the multiplication table, we know that it is a group because it is closed, and you can see that there is C3's inverse is C32, C32's inverse is C3, sigma 1's inverse is sigma 1, sigma 2 inverse is sigma 1. So everyone has an inverse and we have an identity. So it is a group. Now you can ask a question, is it an abelian group? Suppose if you take C3 to sigma 1 is sigma 3. Now sigma 1 C3 if you take, it is sigma 2. So it's not an abelian group. So as I told you, the first non-abelian group will come of the order of 6. First non-abelian group will come only in 6th order. So this is an example of a non-abelian group. So C3V is a group, order of this group is 6, and it is a non-abelian group. How many generators are there in this group? Any doubt in filling up? Operations are clear. How are we doing group operations? Is that clear? On the geometrical object? Okay. Over. 10. Okay. How many generators are there in this group? How many generators are there? Two. What are they? How do we define a generator? Any element, when you raise it to some power, it becomes identity. Correct? C3 2, C3 cube is identity. So C3 is one generator. Sigma 1 Sigma 1 square is identity. So sigma 1 is one generator. Sigma 2 square is an identity. So we have 4 generators. Okay, generators are C3, sigma 1, sigma 2 and sigma 3. What is the order of C3? Order of generator is the smallest power. When it raises it to that power, it should be identity. So what is the order? Is 3. Correct? Order of sigma 1 or sigma 2 or sigma 3 is 2. Can we write what are the subgroups it has? Has it some subgroups? Which are the subgroups? From the multiplication table we can get an idea. If you look at this part of the table, if you take this set, it's not going out of this set. So this is a subgroup. Okay. Now if you take E sigma 1, E sigma 1. E sigma 1 is sigma 1, sigma 1 is sigma 1, sigma 1, sigma 1 is E. So these two elements also will be a subgroup. So we have one subgroup H1 is equal to E sigma 3, sigma 3 2. H2 is equal to E sigma 1. H3 is equal to E sigma 2 and H4 is equal to E sigma 3. Normally, the number of distinct subgroups will be equal to the number of generators. Each generator can be used to generate a subgroup. Correct? Each generator can be used to generate a subgroup. So these are 4 subgroups. Now which of them are normal subgroups? H1 is a normal subgroup. Why? You multiply a left coset is distinct from this, then there is only one such set. So right coset also should be same set. Okay, this is another thing. When your order of the group is half of the order of the subgroup, it is always a normal subgroup. Okay, but is this a normal subgroup? Suppose you check that. You take some element which is not in this, let's say sigma 1. So sigma 1 is in G but not in H2. Sigma 2. Sigma 2 is in G but not H2. So what is sigma 2 H? Sigma 2 H2, right? Sigma 2 H2 is equal to sigma 2 comma sigma 2 sigma 1. Let's come to this. Sigma 2 sigma 1 is C32. So sigma 2 C32 is the coset. Now ask what is the right coset? H2 sigma 2 is sigma 2 sigma 1 sigma 2. Sigma 1 sigma 2 is C3. So this is 2 are not same. So sigma 2 H2 is not equal to H2 sigma 2. So H2 is not a normal subgroup. H2 is not a normal subgroup. This is a non-abelian group and hence not all subgroups are normal subgroups. So H2 is not a normal subgroup, but H1 is a normal subgroup. In the same way you can show this is not a normal subgroup, this is not a normal subgroup. We have only one normal subgroup, that is H3. Yes?
Why we are not considering C32 as a generator?
C3.
So take it C32 times and you will get C3.
Yeah.
And then one more things you are getting.
Yeah, so what I am saying is if you have a set like this, A square, A cube is equal to identity. I am calling A as a generator. Suppose if you take A square and a square square and a square cube. Now what will happen? A square square is a power 4, correct? Now a power 4 is a power 6 is identity, correct? So this also, you can call this also as a generator. So any one of them can be generator. It's only a matter of convenience that we write the first element. You could have chosen C32 also as a generator. Okay. Yeah, every if you have a group which generates a cyclic group, every element could be called a generator. Okay, except the identity element. Yeah, but if I say C3 is a generator, in the elements in the subgroup generated by C3, C32 is already there. So you either call C3 or C32, not both. Okay.
Is there any order for writing the?
These will also get shuffled. Okay. There is an interesting group which I somehow missed defining it. I will define it in the tutorials. It's called permutation group. So if you take any n numbers, then you permute them. Each permutation is like a group element. You take set of all permutations, it will become a group of order n factorial. There will be factorial n permutations. So the order of a permutation group of n symbols is factorial n. So there is a permutation group, and so what happens if you reshuffle them, then these things will just get reshuffled and you will not have any difference. So it's fine. As a set they should be same.